everybody. Some people are still getting in. My name is Carola. I'm from Hamburg in Germany. And my main topic I love to talk about is technical debt. And later on today I will talk about domain-driven design, which is quite related, but another topic. So now we will talk about technical debt in software architecture, and I will show you what I've done in the last almost 25 years of my career. I've studied computer science and did my diploma in 1995, so I'm quite some time on the market now, and I have been there when Java was born, and I have lived in times when there were no unit tests. It didn't exist, When I came into computer science, I started with BASIC and had a Commodore C64 at home, fighting with my brothers to use the television to program. They wanted to watch some films. So in our family, everything was a bit the other way around. I liked computers and they didn't. But anyway, I'm a big fan of jokes, and this is a very cool joke about software architecture. Underneath it says, a good architect leaves a footprint. This is what we all want to do. We want to leave a footprint in life, in our work. And they look at this thing, which seems to be some layers of some software. And the one person says to the other, we gave up finding proper names for the layers long ago. Since then, we just name them after their architects. And here you go. Business rules, transformation, transport, David, Mark, Judy, and John. So this is what I see a lot. But the nice thing about the joke is there is a woman in there, some Judy architect, which is really nice. Okay, this is all about the female topic. I want to talk to you about technical debt. And what is this, technical debt? Well, technical debt is a metaphor in the end that was coined by Ward Cunningham, known for a lot of nice stuff that he did in computer science. And he invented this metaphor already in 1992, so it's quite a while ago. And he said, this happens in software if you decide something on your design or on some technical resources you are using or whatever, and later on you find out this was not a good idea and you have to pay for that. Well, in finance you pay interest. In computer science you may pay money too, because you have to pay someone to do the refactoring. From my point of view, technical debt is something very normal. It happens everywhere all the time, and it's not possible to develop software without technical debt. And I try to squeeze this whole idea into a diagram that I will show you now. And it looks like this. I'm going to explain it to you. Imagine you had the greatest team ever. 5 amazing Java developers, a very, very good product owner, and even a great manager that understands about software development. And you created the most wonderful thing ever, software, and you release it. So you started with low technical debt down here, in the corridor of low and stable maintenance cost. And then, because your software is so wonderful and your users are so happy with that, what will happen? Well, they will use it a lot and they will find bugs and they will ask for more features, please. And of course, you will do it. They will pay you, so you will do it. And the normal thing that happens then is that with the first enhancement that you're doing, you create technical debt, because the first idea of a solution is never the best one. You know that. You do something and later on you think, I should have done it that way around. And this is what this yellow arrow means. If you do maintenance and changes, you will put in technical debt, but because you have this wonderful manager, he will give you money to do refactoring to improve your architecture. Every time. I don't know how it works in your company, but in my company, we are 120 computer scientists, and I'm the boss, and I know about it, and they always have 20% of their time to do refactorings. Who has this here? 20% refactoring time? Yeah, oh, some of them, yeah, okay. Your boss should do it, okay? Tell them. Anyway, if your boss is great, you will stay in this corridor of low maintenance cost, which is great. It's wonderful, and I have seen teams with Java systems, huge things, and they were still in this corridor. It is possible, okay? 15 years old, 20 years old, it works. If not, you start to walk up here, you start to accumulate more and more technical debt, and well, it's not just the color, but if you look at it, you see that the arrows get smaller and smaller. And this means that for the same budget or for the same time, you achieve less. And you probably lived through that once in your life, in your work life, that you try to change something and it gets more and more difficult. So by the time the architecture is eroding more and more technical depths, and finally you are up here in the corridor of high and non-predictable maintenance cost. This is a very horrible situation. I hope you never got in there. If you have a chance to refactor, you can come down to the corridor of low and stable maintenance costs, but sometimes it's too late. And then this happens. This thing is called the Kreb Cycle. The C stands for create. You create something. The R stands for refactoring. The A stands for abandon, because at some point nobody wants to change it anymore. And the P stands for replace. Okay? So this is the Kreb Cycle. A lot of companies try to do that. I was there when Java was born, and these were times when people were telling their managers, well, this whole COBOL, PL1 stuff, all these old things, this is crap, we can't live with it anymore. Please give us money, and we will do it again in a better version. We will do it with Java. And the managers, they trusted them, and user interface was nicer and all that stuff, web, and they gave them money. But now we are at that point again with a lot of huge Java systems. And unfortunately, those managers that gave us the money 15 years back, they are still there. We can't tell them the same story again. So the Kreb Cycle, I don't know if it really works for you. Every now and then people are calling me when they are up here. This is rather late to help, but I can help them. But I have been searching for a picture to explain their feeling, and I found one. From my point of view, they feel like this, They are doing whatever they can that their baby is surviving, I mean, you're visiting them, and they're like, I got up last night at 1:00. I do that all night, every night, to restart some processes, the server, whatever. It's exhausting, they're doing everything for their baby. But the managers, they say, well, they don't see it, They are looking, the managers are up here, and they are looking from above, and above the tree is green. And this is this feeling, well, it works, you're doing it, so why are you complaining? But the situation down here is like this, and this is something managers have to understand. I don't know, are managers here? No. Well, please, if you have any talent for it, become a manager, okay? There's such a lack of technical knowledge in management these days, and they don't know. So this is the situation in a lot of companies. I'm not going to ask you, but yeah. Well, what have I done until now? I have looked at a lot of systems of different types of programming languages, around about 300, 350 now, It works like this. Someone calls me, Carola, could you come by? Yeah, well, what is the problem? Well, our system, we can't change it anymore. It's so hard to change it. Okay, what do you have? Yeah, we have 3 million Java. Wow, it's okay, I mean, I have seen 15 million Java. I know there's 40 million Java out there, so 3 million, it's okay, Well, how many people are working on it? Well, we have 30 programmers. And what are they doing? I mean, I say, well, they are doing maintenance and they are enhancing the software, I guess. No, this is the problem. They are all just fixing bugs. Oh, I said, well, this is a bit too much, 7 people should be enough for 3 million lines of code. So this is too much, and this is a good point for me to help them with their technical depth. The problem with these large systems is that people can't know everything, all the corners in the system. A good programmer, like you, all of you, can keep 30,000 lines of code in their head. This is what you can. This is the capacity of your brain. So if you change something here, you will remember that there was some other area where this change could maybe have an effect. This is what you can. But if you imagine, 30,000 lines of code is nothing compared with the software which is out there. Even a small app on an Android phone has 60,000 lines of code, So you can never know everything, and this is what happens to all of us. What do we do? How do we spend our time? Well, 70% of our time as programmers is spent in understanding what is already there. Maybe you are lucky and you are part of a team that is creating a new software, but this doesn't happen so much these days. Most people have to understand code that is already there, and then you solve the problem, and then you program a bit. So I asked myself in my doctor thesis, I have been writing about complexity of software architecture, how can we help people? Because, solving the problem and programming is just a small part of this cake. Most of it is code comprehension. And what can we do? How can we create software that is easy to comprehend? In this part, we can save time. And this is why I looked into cognitive science. I looked into cognitive science to find out what helps our brain to quickly find our way in huge structures. And I will shortly take you to cognitive science. It's very easy to understand, and tell you why software should be built in what way and what this means for technical depth. Well, our brain is able to do 3 things. We do something which is called chunking, we love hierarchies, and we love schemata. What is this? Well, chunking means that in our brain, we all the time put things together. We hear small things and we put them together in larger chunks. Well, you're doing this as well. Your brain has something between 7 and 9 digits, and my sentences have more than 7 to 9 words, so you are chunking the whole time. The point with chunking is it only works if the things presented to you are linked together. They form something consistent. If they are just near to each other, this doesn't mean anything, What do we do if we try to chunk this? Well, a seal and a stone. Well, the best I can do is maybe beach, but it's not very specific. And this is the point. We have to create chunks in our software that programmers can easily put together, chunk and take as one whole. So we actually, in software development, in computer science, we have a very, very cool concept that is actually pointing to that. And it's something you all know. It's called modularity. So if we want to have a complex structure where people find their way around easily, we have to support chunking, and we can do this with modularity. The others are coming later. And modularity is such a great concept. You probably all learned it, but I will start with a joke, okay? This programmer says, well, it's crucial to find a good name for your class which reveals its purpose. Purpose is something very important, to have something which is consistent. And then they look at the screen, and then the other one says, like crap, I don't know where else to put in. And the other one says, exactly. Well, at least he gave this thing a proper name, you know? I mean, yeah. Naming is key. So this is the point. All these jokes are in the internet. They are done by a Hamburgian computer scientist. Well, what does modularity mean? I want high coercion. I want things that belong together and that are loosely coupled. Maybe you know about responsibility design, which was created in the 90s as well. Separation of concern is a different story. This was Rebecca Worthbrook, and the single responsibility principle, you probably all know Robert Martin and his solid principles. And the first one is the single responsibility principle. So if you want to help your colleagues who run later into your source code, give them pieces of software that have one responsibility, a proper name, so that you understand what they do. Coercion and coupling are really wonderful concepts to explain that. And the best thing for me to explain it is with packages and classes. Imagine you create a package, and the classes in this package are supposed to do something together, to have one responsibility. So this means, I hope, that those classes will work strongly together. They will be coupled, but they should not need anything from the outside. They are not coupled to anything outside of this package. This is the idea of high coercion and loose coupling. This is what we are supposed to do. And then we help ourselves. I don't know, did this ever happen to you? The other day I programmed some algorithm, and I felt so great, you know. I thought, oh, well, this is the best idea I ever had. Perfect abstractions, perfect algorithm, wonderful. I will never forget this great idea. You know? Then for 2 months, I did something else. And then I came back to this thing, you know. And I knew that I thought I would never forget. But I forgot, you know. This is horrible, isn't it? And it happens to all of us. And this is why we really, really, really have to take care of our software. So modularity is the first thing. Hierarchies, well, this is very easy. Cognitive scientists, they did a lot of tests, and humans are better in remembering stuff when it's organized in hierarchies than in nets. A net is for searching, a hierarchy is to remember stuff. They did a lot of tests, and this is something which is proven, and this is something you should as well do in your software. You should have hierarchical layering. The I is missing. Okay, whatever. I see my mistakes. Well, but the best thing that your brain is able to do is that you're working with schemata. What is a schema? A schema is an abstract idea, a concept that you have in your brain about the world and about whatever you see outside in the world, and you have prototypes in your brain. So if I tell you my parents were both teachers, the teacher schema will start to work in your brain, and you remember your teachers in school, and maybe you think, oh, this is why she is talking so much. Or you think, well, must have been a horrible childhood with 2 teachers, you know. Something like this will happen. If I tell you why my father was a hammer, There's nothing, no schema, question mark, what is that? Well, hammer were people, before we had trucks and trains and lorries and airplanes, that did the transportation of goods from Germany to Italy, forth and back, across the hams of the Alps. So this is a hammer, a person transporting goods through the Alps. Now you know it. Now it will not work anymore. But it was about the first feeling. Well, and what the cognitive scientists did as well is they did a test with a chessboard. I know it's the wrong way around, but don't worry. They took the chessboard, put the figures on the chessboard, and showed it to someone who is good in chess. And they said, well, look at it for 20 seconds. Then we take the figures off, and you have to rebuild what you saw, And they did this with very good chess players and with people who don't know anything about chess. And the result was, as expected, the chess players could put back the double amount of figures than those who didn't know anything about chess. But only if on the chessboard the setting of the figures was a reasonable setting in chess. If there was a rubbish setting, nobody, they were all the same. What happened? The chess players used their schemata to remember what they saw on the chessboard. And if this was all in chaos, they were not better than the people who don't know anything about chess. And this is the other point about schemata. They make us much quicker in remembering and understanding, in seeing things. And the great thing is that in computer science, we have something like that. We have schemata. In our language, they are called pattern. I'm very sure that you've learned something about design pattern, architectural pattern. Yeah? Did you? Yes. Great. Because this is such a great concept, and this will help anybody to find their way around in our software if, and only if, we use the pattern in a consistent way. The other day I was searching a bug in a software with a colleague of mine. We looked in the user interface, we found the service, and then we found a class that was called factory. Do you know the factory pattern? This is a pattern, a quite old pattern we used a lot before we had dependency injection, and it was used to create objects. A factory creates stuff. A very, very good metaphor. And we looked at this class, and, we thought, it's a factory. But then we saw, it created business objects, value objects, but it calculated and it processed. It put business objects into the database. What is this? My colleague was, who did this? And I said, well, slow down. Maybe it's just the wrong naming, maybe, we will see. But the point is, a wrong use of patterns slows everything down. Then they are useless. So please don't do it, And if you have patterns in your software, discuss them with your colleagues so that you all have the same understanding. This is something I have very often. I do a lot of analysis with teams, not that large, but like 10 to 20 people, a bit like what we had in the keynote this morning, mob architecting. So we sit all together and we discuss what we see in the software. And patterns are so amazing because then in a group with 20 people, you can be sure someone says, we always do it with this pattern. And then someone on the other end of the room says, what? No, we always do it with this pattern. What? And then they start to discuss, and then you find out what they actually do. So please work on your patterns. So this is what we need in a well-formed architecture to help people use their cognitive mechanisms to find their way around in the source code. We will start now with hierarchies, and I will show you how it looks like in software. In the 90s, when I finished my studies and I was teaching students as well, we just talked about one hierarchy in software. We talked about technical layering, you know. There's a user interface, a business logic, and so on, you know. And it was worth it, because before people were programming SQLs into the user interface. I don't know if you remember. These were the horrible times of discovery, you know. But today, this is not enough to have a technical layering. We actually have to talk about domain modules and think about a kind of layering between them too. We want some base domain modules and some other modules that are built on top. And I will show you an example now of a system that I looked at some years ago, a Java system. The architect called me and he said, well, Carola, can you come? We are heading towards a huge enhancement of our software, and I'm not so sure what they did in the first version, you know. I said, yeah, sure. How big is it? Well, it has 100,000 lines of code, which is small, you know. And I said, okay, I come for a day, I work with them, and then we will see. And I worked with them. There were some problems in the technical layering, you know. So we discussed some violations and repaired them. I mean, we discussed what to do to repair them, and they did it. And I told them, well, listen, your chief architect said you will program now for a year, and then I'll come back. And then I don't just want to see a technical layering, but I also want to see some domain structure and a layering in there. And this is really cool. If you tell them that you are coming back, they'll do it, you know. I will now show you what they did. And I will show you now some pictures from tools. I will explain to you, you will easily understand. This is of a tool called Photograph. If you want to see it in action, you can go to the website of my book. I will put in the link later. I have put some films there. I have not actually translated them to English yet, but you can see the action. That's a good story. I just have no time. So what do we see? This is the technical layering. And the layers are actually here. Layer 1, layer 2, layer 3, layer 4. So this is the user interface. This is the business logic and some other stuff down here. So this is the first place. Then you see those square things. This is something that we did with the modeling tool, with the Photograph. We modeled them onto the system. The tool parsed the bytecode. It knew about the classes, the packages, and how they were connected, but obviously not about higher structures of the software. And this is what we did. So we took package trees and put them into those squares. If you could look inside, you would see package trees with classes in there. And these arcs here, those are the connections between the classes, which means up here in the user interface, in this module up here, there is one class, or several classes, that are using something from down here. This is what the arc means. The arc on the left side is a downwards connection, and the arc on the other side, which is red, is an upward connection. So after a while, you're very quick with those pictures. And we looked at this first modeling, and this is actually great. You know, there's not much on the right side, a lot on the left side. So we looked at those those arcs down here, and it was funny because we looked inside, and you will know why I changed the color to yellow later on. We looked inside and we saw someone used the implementation class and not the interface. And the architect said, oh, here we are. It's just a problem we can quickly fix. We can write impl behind the name, you know, and then it works, you know. Cool. Yeah. So I said, cool, very easy refactoring. Write it down on your list of refactorings. And I changed the color of this arc to yellow, which means I have looked at it. We took the next one. It was the same problem. We looked at the next one. It was the same problem. What happened? They did copy and paste, Cool. We all do, And, well, from one point, from one side, this is a very good story of a pattern for a violation pattern, which means that it's easy to fix. But imagine this would go on. We would not have found it. It would go on and on and on. And after a while, people would think it has to be like this, So whenever you run into a little mistake in your source code base, please follow the Scout rule. You know the Scout rule? Some are nodding. The Scout rule means scouts, if they go and have tents somewhere in some area, they have to leave the place afterwards in a better shape than before. They have to collect all the rubbish, even the rubbish that was there when they came, So please, you can't fix everything, but if you change a class and there is something in there which is not good, repair it. This is something you should do. Otherwise, it becomes normal. And then we had this one here. This something in the business logic is using the user interface. The architect looked at it and said, I knew it. This is the reporting component. I knew something was wrong with it. Please give me the picture. I will go to my boss and I will really ask for money for this refactoring. This is horrible. And I said, yes, you get the picture and then you get the money and you do it, So, but this is not much of a problem. They did a good job and I told them, And then we took the same modules and organized them from a domain point of view. So this is the basic parts of the domain and other stuff that is built on top. And when we had this, I told them, you are really great, There's only some little bits and pieces here. The reporting component is up here again with a problem, but this is really good work, This is the effect, If I come back later. Well, now I show you another story, which is a bit less amusing. I have worked for a client who has a 7 million lines of code Java system, and they have releases 4 times a year on the weekend. All the 100 programmers have to come to integrate, and all the people who are doing the tests have to come, and the users are there too. And if they are lucky, Saturday night, they can have a release party. If they are not lucky, Sunday is gone too, And I asked the chief architect, well, what is your plan if everything goes wrong, He looked at me and he said, well, our strategy is to go forward. I had to think about it a bit because it's quite a positive story, to go forward. But then I realized, well, he can't go backwards. His whole team, 100 people, programmed for 3 months to get this thing done, and the users are waiting for the features. He has to go forward. And his problem came from this. On the left side, you see the technical layering we did for the 7 million lines of code system. And, well, I had told you red is not good, green is good, so this looks good. But one thing I didn't tell you, the pieces, the modules that are darker, there is more in there than in the lighter ones. And you can see that this one is very dark. So this is the business logic. And in this layer, so this is something like 4 million lines of code of the whole system or even more. In there is this, this monster. This is what domain-driven design calls a big ball of mud. We didn't even do any modeling. I just asked the tool to organize the packages in a way that those that are up here are not needed, and those down here don't need anything for up. But you can see the big ball of mud. So all those components need each other. It's like 90 modules in the whole system that need each other, and you can't deploy one of them without the others, you know? And this is what we have a lot in big systems. I look at it on this level, and I often look at it on the level of classes too. I once was an architect for a system that was produced by another company, and well, they found out that I could look into their software, and they gave me the chance to do it. And it was a C++ system, and well, it looked like this. These are all classes, all classes, and the green ones belong to one component, and the yellow one, the lilac ones to another one. Up there, some orange ones, and this is a class cycle, so you can pull wherever you want, and the whole thing follows. You know, you cannot cut anything off. There is no idea of top and bottom or anything. So I looked at it and I told them, well, listen, this is not too big. You can do something about it. Cut it. Think about what these classes are doing. What is their job? Where do they belong? And put them in a hierarchical order, you know. And then they said, yes, we will do it if you pay us for it. And the boss of the company using the software said to them, are you nuts? I ordered high-quality software. I'm not going to pay you to repair that. Well, and then the other company said, okay, yeah, we understand. It's our job. Okay, we do it sometime. 2 years later, the thing looked like this. It turned into 372 classes, all connected. And look, this one, it's now here. You know, it's in there too. This is what I call a black hole, you know, because it's eating classes. Imagine your boss comes by and asks you, could you please do another blue one? Well, my answer would be, must I, you know, because I know this thing is really difficult. You know, I change something and then it falls down at the other end. And my boss says, yeah, we are paid for it. Just do it, you know. I don't know what you do. I copy a blue one, you know, and just change what I have to change, and I hope it will survive. And then I'm in there too, you know. This is what's happening. They grab classes, they get bigger and bigger. They are really like black holes. You know why it's black in there? It's black because in the middle of this diagram are the classes with the highest number of connections. So all the arrows in the back here, there are so many that it's black. This is high coupling and the feeling about a thing like this looks like this. This one says, I cannot reproduce the bug from yesterday. And then they are looking at each other. And then the other one says, well, maybe a time-space discontinuity has come by and moved us into a parallel universe where this bug has never existed. And then they smile. And then he says, well, sounds reasonable. I close this bug, you know. I showed this joke sometimes to some users. They don't really like it, you know. Well, okay. So, first thing, if you want to help your fellows and yourself, try to avoid these cyclic structures, not just because they are cycles, because they are tangled, but also because of modularity. If you think about modularity, and what I was talking about classes or packages that have one job, okay? Imagine you create a class with a basic job, and you build something else on top, and another one on top. From the point of view of modularity, it is not reasonable that the class which is doing the basic job needs anything of the classes on top of it. Okay? So cycles are actually a bad sign against modularity. We will look into modularity now. One problem that I see very often. People are calling me, "Oh, Carola, yeah, can you come?" And I said, yes, I can come. What do you have? Well, we are trying to divide our system into microservices. You probably know that problem, no? And I said, okay, I can come, but what's your problem? Well, we are not really getting forward. Okay. Why? Well, the whole thing is so tangled. Okay, I say, well, let's have a look at it. And, I will jump one picture further. This is something I see a lot. This is a system just in a different style from a different tool. I will explain to you. I was in a company, and they created a system to have in their Java source code to have modules, a bit like Maven. It was like some time ago they did it. I'm not going to name the company because bad stories are always without company names. And I talked to the guy, and he had 2 million lines of code of Java. And I said, well, I understood that in your system you have components. Yes, he said. And the idea of their components was to be cycle-free. No cycles in the component structure. And I said, okay, how many components do you have? And he said, well, we have 9. And I said, okay, show me where they are. And he said, well, could we just do it in the right way? And I said, what do you mean? Well, actually, we have 17. Oh, I said. And then we modeled them. And in there is packages, classes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, there they are. And the 9 components are here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And this is 80% of the system. And why? Because when they did the first programming, they didn't have the component system, and they created cycles over cycles, and nobody gave them money to repair it. Of course, you can go to your boss and tell him, I have 9 cycle-free components, but if you have a monolith where 95% of your source code is inside, and the rest is very small, this is not worth all your work, you know? So please look at your modules, at your Maven modules or whatever you have. Are they similar in size? Look at the big classes. The other day, I was at a client with 9 million lines of code, and he said, well, I only have half a day. Just do whatever you do so that I see that it's useful what you're doing. And I said, okay. 9 million, normally this is like 4 days of work, you know. I asked him, how many build units do you have? And he said, 128, which is not enough for 9 million lines of code. And then we said, okay, can we just have the number of classes per build unit? And this is what you see here. And this is one build unit with 9,240 classes. Compared to the others, there's something wrong, isn't it? And on top, if you look at the lines of code, it has 3 million lines of code. This one build unit, but 3 million lines of code is a third of the system. And the number of classes is not a third of the system. You see it? What happened? Big classes. And then we looked inside of that thing, and we found something I have never, ever seen before, really. We found a cycle of 5,270 classes, all like this, you know, all linked to each other. This is the largest class cycle I have ever seen in my life. And we looked at it, you know, we found it after 2 hours, and we said to the guy, well, what are you doing with this? This is horrible. And he said, no, we are not doing anything with it. We created an interface, you know. In domain-driven design, this is called an anti-corruption layer. So a third of his system he's not touching anymore, you know. Horrible story. Okay, so the last thing was pattern consistency. I really, really hope that you do pattern in your software. In each domain module, you should have patterns. I just put some here on the slide. UI patterns, model view controller, you probably know. And the cool thing about patterns, and this is the point, patterns are describing the responsibility of a class, and they are explaining who should work together with whom. Imagine you know the model view controller pattern, and somebody is trying to get you to program into a view a call to a service. You would know that this is wrong. Huh? We're not going to let the view call the service. This is nothing we should ever do. Or somebody wants you to program into the model some UI bits and pieces, some fields for the UI. You will not do it because you understood the pattern. And this is the point. Patterns help modularity and they help hierarchies. So they are really wonderful things. And if you look at software from that point of view, this is very funny. When I get somewhere, I ask them, what is your architecture? And the normal answer is, well, we have layers, technical layers. And then I say, okay, let's check the technical layers first. And then we look at those violations, those red arcs in detail, and we discuss the violations, And then if someone says, what? A service is not allowed to do this. A service is not allowed to call the controller. I know there are patterns in the software. And I start to discuss the patterns with the teams. And often we use some board to do it. We put them there. We discuss the relations, what is what, and so on. And then we check the patterns with a tool. What do you see here? You see layers, a service layer, a process layer, and so on. But if you could open it and could look inside, you would see that in this service layer, there are only the service classes of the system. We collected them with regular expressions or because they have they inherit all from some superclass or they have an annotation, like in Spring or whatever. So only the service classes in here, only the process classes in here, although they are lying in the same package in your software, So it's a different view on your whole source code. And this team was very good with his patterns because the patterns are hierarchical. You expect only usage on the left side, so very low rate of violations, just 0.1 violations between the patterns. And the question is always how much of the system is following patterns. And this team was great, 90%, I'm sure whatever you have in your software, the classes that don't follow patterns are the worst, are doing the most rubbish in your system. Look at them. One other well-known story, of course, is the util area. But util is sort of, I don't know, people understood that util should be really dumb and, not. But there is some new idea these days. People are doing something else today, and I guess you know it. I will show you. These are classes. And there's a plugin manager who knows his load command, and the load command knows the plugin manager, and so on. The script command knows the plugin manager, and forth and back. And, well, this is something that you find a lot in old systems. Some class in the middle and some other that know this class. This is as well a problem that was created before dependency injection. And if I find them, I just leave them alone. But this one is connected to another problem. If you go over here, you find a plugin properties class, which is normally something very stupid. You get properties from that thing. But what is plugin property unfortunately doing? Plugin property is calling a class that is called property helper. Helper classes are the new util, And the problem is not the name. I mean, the name is the problem because, well, I'm just helping, you know. I can help anybody, anywhere. But this name doesn't explain what's the role of a helper class in my structure. Because this stupid helper class is calling the plugin manager. And there's no rule that the helper class is not supposed to do it. Please don't go home and rename all your helper classes, okay? This is not what I want. But think about the rules. What is the job of a helper class and to whom should it talk and talk not? Then this will not happen. But helper class is really dangerous. One last joke, 2 slides, and we're done. This is very nice. Best practice in application architecture, use layers to decouple. And he says, and every year we mount a new layer to decouple us from the crap we've done the year before. You might know that. But the best thing about this joke is down here it says annual rings. You know, trees have annual rings. You know that, you know. The other day I was in a discussion with an architect and his boss, and I said, well, listen, your system, it has too many patterns doing the same thing. You know, you have to sort of put some together and give them proper names and so on. And the architect said, yes, I understand. But we can't do it. Oh, I said, you can't do it? Why? Well, listen, our developers, they are artists. They have to invent and use new patterns every year. Otherwise, they are not happy. You know, our software has annual rings. And I looked at him and thought, wow, he's using a positive concept, you know. I mean, trees with large annual rings are healthy because they got enough water in that year. But for software, this is not healthy. I'm sure all software systems have annual rings, but it's nothing to be proud of, okay? So be aware what patterns you have and use them consistently. No cycles, responsibility and modularity. And, well, I'm talking to you, but I'm very often talking to managers as well. And they always ask me, well, now, how good is our system or how bad? And finally, we came up with the Modularity Maturity Index, which means that we give systems grades from 0 to 10, how modular they are. And if you're between 8 and 10, you're green, and this means you're good. You're in the range of low maintenance. If you're between 8 and 4, there is some hope, and under 4, it's a disaster. And, well, what you see here there's one system per step on the x-axis. What you can see here these are systems in Java, C#, PHP, whatever. And this is a Java system, and this is a Java system, and this is a C# system of 10 million lines of code that is created in Romania. So it has nothing to do with where the people are from, what language they are using. It has only to do with the understanding how to create a modular system. And I hope you're not going away like this now. And if you want to know more about it, my book is now available in English. You can find it on Twitter. And this is the link to the website where you can watch videos. I promise to translate them next weekend. At the moment, you hear my voice in German. You know, but you see the video. Thank you.